Global shipping pushes millions of tons of steel across the ocean every day, and maintaining that momentum requires burning enormous amounts of heavy diesel, which pumps thick, black exhaust directly into the atmosphere. Moving any massive vehicle requires a lot of energy, but ships face a unique hurdle. Unlike a truck driving on a highway, a ship operates in water, a fluid roughly 800 times denser than air. Understanding exactly how this dense liquid slows a hull down goes back to 1861. An English engineer named William Froude began towing wooden planks through testing tanks to measure the opposing forces. Through these tests, he realized that a moving ship doesn't only lose energy by pushing water forward out of the way to create waves. An immense amount of drag comes simply from the friction of water sliding aggressively against the hull's wetted surface area. This diagram shows the two distinct problems naval architects have to solve: wave-making resistance, which is the energy lost smashing into the bow, and frictional drag, which is the water physically scraping along the sides and flat bottom of the steel. This data visualization shows how those two drag forces are distributed. For massive merchant vessels that travel at lower, steady speeds, the wave-making penalty is actually minimal. Instead, the lateral friction sliding against the wetted hull is the absolute dominant force, making up to 85% of the ship's total drag. Because of this density, cutting down microscopic surface friction is the single most effective way to lower a ship's fuel consumption and improve its economic margins. In 2011, the International Maritime Organization rolled out a sweeping measure known as the Energy Efficiency Design Index, or EEDI. This strict environmental standard mandates that global fleets drastically cut their greenhouse gas emissions. For shipbuilders, the most viable path to hitting these EU targets is to lower the hydrodynamic drag on their vessels, meaning the massive diesel engines won't have to burn as much fuel to maintain speed. The maritime industry was forced into a corner. They needed a way to bypass the physical friction of the ocean without entirely redesigning the complex, expensive cargo fleets already on the water. The answer came from an unexpected place. After World War II, the U.S. Navy experimented with systems that continuously injected air around submerged hulls. Their objective wasn't fuel efficiency. They wrapped their vessels in air to acoustically mask internal engine noise, preventing enemy sonar from tracking them. But as fluid dynamicists reviewed the performance data, they noticed an incredibly useful side effect. The protective air blanket surrounding the hull was drastically reducing the ship's frictional resistance. Engineers pumped a continuous sheet of air under the flat hull to physically separate the dense ocean from the steel. However, as the ship pitches in rough seas, the heavy hydrodynamic flow violently rips that air blanket away, faster than compressors can replace it. Trying to maintain a single, solid sheet of air is entirely too fragile for the unpredictable dynamics of the open ocean. To protect the air layer from washing away, Russian naval engineers developed a second aeration. They altered the actual structure of the hull, building inverted physical recesses, called partial cavities, directly into the bottom of the ship. Much like an upside-down drinking glass pushed into a bathtub, the geometric recess physically traps the air. Shielding the layer this way cuts the energy required to maintain the pocket by a staggering 2/3. While highly efficient, this method requires hollowing out massive sections of the ship. For a commercial freighter, that means sacrificing highly valuable cargo capacity and introducing complex structural weaknesses to the steel frame. Because of these flaws, the shipping industry ultimately pivoted to a highly adaptable third option. Modern air lubrication systems use thousands of tiny vents to actively inject millions of microscopic bubbles into the boundary water. This diagram details the shift in fluid dynamics. The microbubbles aren't trying to build a solid physical wall between the ship and the sea. Instead, blending air into the boundary fluid actively alters the physical density of the water itself. Less dense fluid creates less friction against the steel. This approach reduces drag along the curved surfaces of the hull without forcing shipbuilders to compromise the structural integrity of the vessel. Making this system work requires immense precision. Hydrodynamic tests prove that for peak efficiency, these injected bubbles must be kept incredibly tiny, often less than 1/10 of a millimeter in diameter. This animation shows the buoyancy threat in action. As bubbles travel down the hull, they naturally bump into each other and merge. When they combine, increased natural buoyancy pulls them away from the steel boundary and out into the ocean, instantly erasing their friction-reducing benefits. Controlling this microscopic fluid dynamic dance, keeping the bubbles small and tightly hugged against the hull, is the absolute baseline for making the technology viable on the open sea. Because the microbubble system relies on small vents rather than structural hull changes, it carries a massive commercial advantage. It can be easily retrofitted onto the flat bottoms of existing cargo fleets. But the laws of thermodynamics dictate that you do not get energy for free. Pushing millions of bubbles down into the dense ocean actively requires electricity, meaning the ship must burn fuel to run massive, heavy-duty auxiliary blowers and compressors. Air lubrication is an active, ongoing equation. The propulsion energy saved by reducing friction must ultimately outpace the energy spent to generate the bubbles. This visualizes strict EEDI accounting. When calculating efficiency gains, mechanical fuel burn to run the compressors is subtracted from the total propulsive fuel saved. Even with this penalty, independent sea trials prove microbubble systems can generate net energy savings up to 10%. In an industry where a single vessel routinely burns hundreds of tons of fuel every day, a 10% drop in consumption yields colossal financial savings and keeps millions of tons of carbon dioxide out of the atmosphere. By adapting Cold War acoustic technology and validating 19th century hydrodynamic physics, engineers have figured out how to let massive mountains of steel efficiently glide on a cushion of air. They are actively manipulating the physical density of the ocean itself, guiding global shipping toward a cleaner,